Hi, thanks for joining me. Today I'm going to be showing you a really cool theorem due to Euclid, who's mostly known for his work in geometry and to do with prime numbers, or at least his proof that there are infinitely many primes. Today we're going to be looking at a theorem which is a bit to do with prime numbers, but also to do with perfect numbers. So just to remind you, a perfect number is a number whose proper factors add up to itself. So for example, 28 is a perfect number because if I look at the factors of 28, or the proper ones, i.e. the ones that aren't 28, I get 1, 2, 4, 7, and 14, and if I add all those up, I get back to 28, and hence 28 is a perfect number. Now, what does Euclid's theorem say? It says that if you let A be the set of prime numbers P, such that 2 to the P minus 1 is also prime, and B be the set of perfect numbers, then Euclid's theorem says that the cardinality of B is at least the cardinality of A. So in other words, the size of this set is bigger than or equal to the size of this set. So there are at least as many perfect numbers as there are prime numbers P which have the property that 2 to the P minus 1 is also prime. So pretty interesting property to have, or a pretty interesting result to have. Let's get into the proof of this theorem. Okay, so the way that we're going to prove this is by showing that there is an injective function from A to B. So in other words, if we take a number in A, there's a corresponding element in B, such that, it's a unique corresponding element in B. So therefore, the number of elements in B must be at least the same as the size of A. Okay, so what is this function? Well, let's suppose P is in A. And then what we're going to do is define the number n, which is obviously going to depend on P, to be 2 to the P minus 1 multiplied by 2 to the P minus 1, like so. And this is going to be our corresponding number. And I claim that this number here, n, is in B. And I'll prove that in just a moment. But if I can do that, then that will mean that we have an injective function from A to B, because clearly this thing here is going to increase as I increase P. So this is a strictly increasing function. And so therefore, if you think of n as kind of like a function of P, this is an injective function. In other words, two different inputs of P are going to give me two different outputs for n. Okay, cool. So let's prove that n here is a perfect number. How do I do that? Well, I just need to use the definition of a perfect number and think about the factors of this guy. Okay, so let's suppose f is a factor of n. So f divides n. Well, what are the prime factors of f? Well, if we think about n is a power of 2, so 2 to the power of p minus 1, multiplied by 2 to the p minus 1. But remember, 2 to the p minus 1 is prime. So n only has two prime factors, 2 and whatever 2 to the p minus 1 is. So I can write f in this form. So f is going to be 2 to the power of alpha multiplied by 2 to the p minus 1 to the power of beta. Because f can't have any other prime factors. So for example, if, let's say P was very big, so in other words, 2 to the P minus 1 is not 3, then it's impossible for F to have a factor of 3, because if F had a factor of 3, that would mean N has a factor of 3, but N clearly doesn't have a factor of 3. So for F to be a factor of N, it has to be of this form, where alpha is at most P minus 1, and beta is either 0 or 1. Because the power of 2 to the P minus 1 is, well, 1 in n. So you can't have 2 to the P minus 1 squared and have that as a factor of n. Okay, cool. So we've basically described every single possible factor of n here. So now all we need to do is add them up. And add up all the proper factors of n. So if you add up all the proper factors of n and add them up, it should be equal to n. So if you think back to the 28 example, we had 28 and the factors were 1, 2, 4, 7, and 14. And when we added those up, we got back to 28. What I'm going to do here is also add the number itself. So I'm also going to add 28. And then I hopefully should get that that's 2 times 28, which obviously is the case here. I'm going to do the similar sort of thing here. So I'm going to add up all of the factors of n. So add up all the possible values of f and show that that equals 2 times n, because that's just a little bit easier to do. So let's add up all of these factors. So let's add up all the f's. So that's just going to be summing over alpha from 0 to p minus 1, and then summing beta from 0 to 1, of f, which is 2 to the alpha times 2 to the p minus 1 to the power of beta. Now, I can take this 2 to the alpha and put it there because it's independent of beta, and I get the sum from alpha equals 0 to p minus 1 of 2 to the alpha, and now beta is either only 0 or 1, so I can just plug in each of those values. If I plug in beta is 0, I get 2 to the p minus 1 to the power of 0, which is just 1, and then if I plug in beta is 1, I get 2 to the p minus 1, like so, and the 1 and the minus 1 cancel, and I'm just left with 2 to the alpha times 2 to the p, and so this is just 2 to the p times the sum from alpha equals 0 to p minus 1 of 2 to the alpha. But now this guy here is just a geometric series. The first term is 1, the common ratio is 2, and the number of terms is p. So I can just use our formula here and get that this is 2 to the p times 1 times 2 to the p minus 1 all over 2 minus 1. Now 2 minus 1 is 1, so I'm just dividing by 1, so I can kind of ignore that. This 1 doesn't do anything, and I'm left with 2 to the p times 2 to the p minus 1. And if you think about back to what n was, that was 2 to the p minus 1 times 2 to the p minus 1, which is precisely half of what we have here. And so this is 2n, and so therefore n is a perfect number, and therefore n is in B, and we get the result that the size of B is therefore at least the size of A. And that proves Euclid's result, which is really, really interesting. We can somehow generate perfect numbers from the numbers in the set A. And now if you know a little bit more about perfect numbers, you'll know that, well, at least at the time of recording of this video, we only know about finitely many perfect numbers. And it seems like this relatively simple theorem proves that there probably are going to be infinitely many infinitely many perfect numbers. The only issue with that is, well, we need primes p of the form of A. In other words, that 2 to the p minus 1 is also prime. And it turns out we don't know very many of these. We only know about 50 of these, or I think less than 50 of these. We've just checked that by brute force using computers. So if it turns out that there are infinitely many primes in the set A, then that proves that there are infinitely many perfect numbers, but it could be that there are only finitely many primes in A, in which case we won't know if the number of perfect numbers is infinite or not. Nonetheless, a pretty interesting theorem on perfect numbers. I'll link below another interesting video I think I've made on perfect numbers, which is to do with the powers of the primes in the prime factorization. But yeah, we'll finish off there for today. I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.